Hello, welcome to lesson 5. In this lesson, we are going to look at the calculations using the lens formula. Let's look at this first question. Two thin convex lenses A and B of focal length 5 centimeters and 15 centimeters respectively are placed coaxially 20 centimeters apart. If an object is placed 6 centimeters from A on the side remote from B, find the position, nature and magnification of the final image. And then also sketch a ray diagram to show the formation of the image, of the final image. So let's look at this. It is always good for us when we are dealing with this to use this ray diagram, to understand this better. So here, we are having two lenses, that is A and B, and they have focal length 5 centimeters and 15 centimeters convex, so it means they are all positive. So let's first draw the sketch just to help us understand that, because we're having two lenses. So here we shall have this lens A and B. So remember that the ray, so after drawing these two lenses, we are going to place our object 6 centimeters from A on the side remote to B. Side remote to B means the side far away from B. So if this is the lens, the object can be this side or this other side, but this side will be nearer to B. So the side remote will be this side, so the object will be here at a distance of 6 centimeters from the lens A. So that is 6. So we shall draw, this is a point object, so a ray from the object goes to the lens and then it is refracted. Because this is a converging lens, they will converge. It will be converging. And as it is converging, it meets this lens, the second lens B. But before we consider that, it means that if this lens was not there, this ray was going to converge and the image would be formed at I1. Will be formed at I1. That means that if you want to get if you consider the action of the first lens, we can get this distance from the lens up to I1. So let us first get that. Considering the action of lens A, the object distance is 6 centimeters, the focal length is 5. So using the lens formula, we shall have 1 over f is equal to 1 over u plus 1 over v. And when we replace for f and then substitute for u as 6, we shall get our v as 30 centimeters. So the distance from here up to here is 30 centimeters. Now when we consider the second lens, that is the lens at B, we shall see that this lens, the ray which was going to be going this side is going to be actually again converged by this second lens. It is going to converge to this position. That means that the final position of the image is going to be I2. But now, since the ray was going to this I1, it means that this becomes the virtual object. It becomes a virtual object. So this first image position becomes a virtual object position for the second lens. So the distance from I1 up to this B is going to be the object distance, and it's going to be virtual because the ray actually does not go there. And then the final image is going to be at I2. So when you're considering the action of lens B, we shall have u is going to be, the distance from here up to here is going to be the 30 from here up to here, 30 minus this distance, the separation here, which is 20 centimeters, which is going to give us negative 10 centimeters. So the u is going to be negative 10 centimeters, and the f is 15 centimeters. So using the lens formula, we shall have our v as 6 centimeters. So it is positive, which implies that it's going to be a real image. That's why even this, as you can see, is real. So when you're dealing with this, sometime you may need to work out as you construct. You do them concurrently. So how did we know that this? Because here I know the working here has gone very well with the diagram. because I know that when the ray reaches this converging lens, it's going to converge, and the image is going to be formed, and it's going to be a real image. And even the calculation is showing us this is going to be real because this is positive. So the final image is going to be 6 centimeters in front of lens, the convex lens B. And the magnification, we shall get the magnification of the first lens and the magnification of the second lens, that is M1 times M2, which will give us 30 divided by 6 divided by 6, times 6 divided by 10. So it is 30. Remember the image distance was 30 divided by 6, and then for this one is 6 divided by the image distance, which is 10. So the object distance, which is 10. So that will give us 10. And that will be 30 over 6 times 6 over 10, which will give us 3. So the magnification is going to be 3. Let's also look at this second question. A thin converging lens P of focal length 10 centimeters and a thin diverging lens Q of focal length 15 centimeters are placed coaxially. When we talk of coaxially, it means on the same axis, 50 centimeters apart. They are 50 centimeters apart. If an object is placed 12 centimeters from P on the side remote from Q, find the position and nature, and magnification of the final image, and then sketch the ray diagram to show the formation of the final image. So we can work out first and then sketch, but even it is good also to sketch as we are working out, because that helps you. So especially for the first case, so we know the action. If we consider the action of the first lens, first of all, we know that for the first lens, that is lens P, we shall look at U. The U is going to be 12, and then the F is 10. It is positive, so we shall have our V. Using the lens formula, our V is going to be 60 centimeters. Our V is going to be 60 centimeters. So you can see if we place our object 12 centimeters, it is going to converge, and the image is going to be real. And that is going to be 60 centimeters away from this lens P. However, when we place our second lens, that is lens Q, the final image is going to be at I, because as the ray goes to this, remember this is a diverging lens, and because it's a diverging, remember it was converging, but now it is going to be refracted. It's going to be refracted. So if it was going this way, it's going to be refracted a bit, and it's going to be formed. The final image is going to be here, and it's also going to be real. So we can still work out this and calculate. So first of all, we have already seen that the final image is at 60 centimeters from lens P. That means that we are still going to have the action of the second lens. But now, the image of the first lens becomes the object of the second lens. The image of the first lens becomes the object of the second lens. And that image is here. But for the second lens, it is going to be a virtual image, because the rays actually do not go to I1 when this lens is there. So that's going to be a virtual object. And therefore, the virtual distance there is going to be the distance from here up to here, which was 60, the 60 centimeters, minus the distance from here, P and Q, which is 50. So it's going to be negative of 60 minus 50 when we consider the action of the diverging lens. But also we know that the focal length of a diverging lens is negative. So that means that it's going to be negative 10 centimeters for the U, and F is going to be negative 15 centimeters. Then after that, we are going to apply the lens formula, substitute for F and U, and we shall get our V as 30 centimeters. Shall get our V as 30 centimeters. Then after getting that, remember they want us to get the position, so it's going to be 30 centimeters from the diverging lens, 30 centimeters behind the diverging lens. Then also, it is going to be real, because this is positive, it's going to be real, and it's going to be real. Then they also want us to get the magnification. The magnification is going to be, if you want to get the magnification of the final image, remember this is the final image. If you want to get the magnification, you consider the action of the first lens and the second lens. So we're going to get the magnification of the first lens times the magnification of the second lens, which is going to be m1 times m2, and that will be, remember for the first lens, the V is 60, the U is 12, so 60 divided by 12, and for the second lens, the V is 30, the U was 10, 60 minus 50, which was 10, so that is 30 divided by 10. If we multiply that, we get 15, and the magnification, the required magnification is going to be 15. Let's look at the next question. Light from a distant object is incident on a converging lens of focal length 20 centimeters placed 12 centimeters in front of a diverging lens of focal length 6 centimeters. Determine the position and nature of the final image. So it is a distant object. Whenever we have a distant object, the image is always going to be at the focal point or at the principal focus. It's going to be at the principal focus. So if you consider the action of the converging lens, parallel rays of light are going to be meeting at the principal focus. So the image is going to be, the image distance is going to be the same as 20 centimeters because the focal length is 20 centimeters. So the image distance is going to be 20 centimeters. So action of the converging lens, we are saying that the image of a distant object is formed at the principal focus of the converging lens. So let's see the illustration there. So rays from a far distant object is going to be converged to the principal focus of that converging lens. So the distance from this image up to where the lens is going to be 20 centimeters. However, we are going to place, remember that there is a diverging lens being placed between, 12 centimeters in front of the converging lens. So if I place it here, it means it's going to be between the image of the diverging lens, sorry, the image of the converging lens and the converging lens. So it's going to be around here. So I will place my diverging lens here. So if I place my diverging lens here, then remember that the ray as it is converging here, it's going to meet the diverging lens, which is going to diverge it. It will diverge it. It will diverge it, and the image will appear to come from here. Now, if you want to get the nature of that image formed, we need to, first of all, of course, we know that from the first, we have already got the action of the converging lens, which gave us the image here. And it means that the image here is going to be the object for the second lens, the diverging lens. But now that object is virtual, because remember, these rays actually do not go to this point. They are going to be diverged, and they appear to be, these rays were supposed to be going this way, but they did not go because of this diverging lens. So this becomes a virtual object for the second lens, which is the diverging lens. So if you want to get the distance, is going to be, remember, the distance from here up to here is 20. The distance from here up to here is 12. So this distance from here up to here is going to be 20 minus 12, which is 8. But it's going to be negative because it's a virtual object. It's going to be a virtual object. So U is negative 8, and also F is going to be negative 6 because it's a diverging lens. Substituting the lens formula, we shall have our V as negative 24 centimeters, which clearly shows that the final image is virtual. So the final image is going to be here, virtual, which appears to actually, because the ray is going to be going that side and the image is going to be formed here. The intersection is going to be here. So it's going to be virtual 24 centimeters in front of the diverging lens. So if you talk of the nature, it's going to be a virtual image. It's going to be a virtual image, which is 20 centimeters behind the diverging lens. If you consider this. Yes. Let's look at number 4. Light from a distant object is incident on a diverging lens of focal length 9 centimeters, place 6 centimeters in front of a converging lens of focal length 10 centimeters. Determine the position and nature of the final image. So this is quite similar to what I have been looking into, but this is a diverging lens. But even though it is a diverging lens, still, for a distant object, the image is going to be formed at the principal focus. So the image distance is going to be 9 centimeters. So if you consider the action of the diverging lens, you're saying that the image of a distant object is formed at the principal focus of the diverging lens. And if you look at the ray diagram, it is going to be like this. So a ray from a distant object is going to meet this diverging lens and is going to diverge it. And the ray is going to be diverged. And when it is diverged, it is going to meet the second, because within here there is another lens, that is the converging lens, which is going to converge it to its final position. So we are going to first consider the action of the first lens, which gives us the image at the image is going to be formed at the principal focus. So it is going to be, the ray is going to go this side, but it will appear to be coming from the principal focus. So this is going to be where the image of the first lens is going to be, and this image is going to act as the object for the second lens. So if I want to get the object distance for the second lens, that is for the converging lens, it's going to be the distance from here up to here, which is 9 centimeters, plus the distance from here up to here, which is 6 centimeters, that's the separation, giving us 15 centimeters, and it's going to be a real object for the second lens, which is the converging lens. So let's consider the action of the second lens, and the image formed by the diverging lens acts as a real object for the converging lens, as I've said. And so that distance is going to be 9 plus 6, which is 15 centimeters, and f is going to be 10 centimeters. So applying the lens formula, we shall have our v as 30 centimeters. If we substitute for u and f, we shall get v as 30 centimeters. So it means that the nature is going to be real. The final image is going to be real, and it's going to be 30 centimeters from the converging lens. Let's also look at this question 5. Lastly, I want to look at this question 5. In the diagram below, the image of the object is formed. The image of the object is formed on the screen when the convex lens is placed either at A or at B. If A and B are 15 centimeters apart, the distance between A and B are 15 centimeters apart, find the focal length of the lens and the magnification of the image when the lens is at B. Now this is what we looked at in the previous lesson. Remember, we said that in the previous lesson we looked at the case whereby when the image, we said at this point, when we place the lens here, the image is going to be formed on the screen. Then keeping the screen and objects, keeping the screen and the object in the same position, we are going to adjust the position of the lens until when we find the image again here. So the distance from this object to this is going to be the object distance, and the distance from here up to here is the image distance. Then also the distance from here up to here, we are calling it L. So this, the L is 45, the D is 15, the D is 15, the U is L minus D divided by 2, and the V is L plus D divided by 2. So we can just get the formula. We can use the formula that we derived. That is F is L squared minus D squared over 4L, where L is 45, D is 15. Substitute that, we shall get L is equal to 45 and D is equal to 15 centimeters. And when we substitute, we shall get our F as 10 centimeters. Shall get our F as 10 centimeters. Then also remember the magnification, we had derived the magnification when it is at B, which is actually, when it is at B, remember, when it is at B, this is going to be the image distance, and this is the object distance. So that will give us the formula from using the formula. Remember the magnification, we got it as, when for the second case it was L minus D over L plus D, which is going to be 45 minus 15 over 45 plus 15, which will give us 0.5. You can as well work out this from first principles. Or if not, you just use the formula. Yeah, thank you for your attention. We'll meet in the next lesson.